I'm a really big fan, but I'm not talking about sports teams or TV shows or comic book series turned Hollywood. No, I'm a fan of fans themselves. And I have been for quite some time. My collection is 27 strong. And that's not to mention the fans that are in my computers and servers or behind you in my Kubernetes cluster. It's a lot of fans. You see, when I was a kid, I would ask my dad to buy me fans for doing well in school. In kindergarten, my parents let me stay home from school one day so I could watch some HVAC guys replace our old air conditioner. I then asked them to give me the condenser fan off the old unit, and they were so weirded out by my request that they just had to oblige. This monster of a server fan was my birthday present when I was 11. And when I was in high school, I accidentally stuck my finger into this fan while it was running on a hovercraft that I made out of styrofoam.
All right.
It cleanly sheared off a chunk of my skin. So why am I telling you this? This very clearly strange part of my childhood that I haven't let go of whatsoever. Well, it's because I think fans are interesting. And throughout the years, I've spent time learning about the science and how they're designed. And I can tell you personally that the world of PCs and gaming computers tends to get stuff wrong. Take this computer that I worked on a few years ago. This computer is straight from Dell, like the Dell, big tech company Dell, and they put one fan in this thing. Basically no ventilation holes anywhere on the case, and the fan was moving air from outside across the CPU heatsink and into the case. This computer killed not one, but two of my hard drives. Look, this one dead. I remember writing that on there, being so upset with, it's just stupid. It was stupid. Those drives failed after hitting 157 degrees Celsius. Like that's, you could cook a chicken in that computer. It's insane. Of course, to remedy this, I just took the fan and reversed the airflow so it was blowing air outside of the case. And I tore off the plastic in the front to add a second fan that would blow air right across the hard drives. But still, I mean, it was stupid. Okay, I guess you can make the argument that I should have thought of that before turning it on and using it to mine Bitcoin. I mean, do BOINC research. But I make mistakes. Everyone makes mistakes. I make mistakes. And a mistake that I recently made was using those high-power Foxconn fans in my last PC upgrade. Turns out the cooling performance is very good, like almost too good. It's so good that now I'm kind of like, all right, this is too much, and probably I can make it quieter. I'm usually not bothered by PC fan noise, but I'll tell you what, they can get up there. They can get a little loud. So I'm going to replace my pair of Foxconn fans with this pair of Noctua fans. Really simple, really. But I don't want to do that right away. I mean, after all, I still have like these high power, server fans. Like this one's aluminum. I want to have some fun. What might it do to the cooling performance in my computer? It's a great question. But before I do that, let's talk about airflow and static pressure real quick. I have a Noctua NFF12. I have a Delta PFR 1212 DHE. I have this sketchy power supply that I made from an old computer power supply. Please don't try and build one of these yourself. Please, promise me that, okay? And I have a trash bag. Do you see where this is going yet? So the Noctua here is really perfect for any kind of gaming computer needs you might have. I mean, it's really quiet and due to some really thoughtful engineering, it also provides pretty decent airflow and static pressure, honestly. In contrast, the Delta server fan literally draws 100 times the power of the Noctua fan. It's insane. And its blades also spin 5 times faster, about 7,400 RPM or something like that. I don't remember what the datasheet said. But if you were unfortunate enough to accidentally get your finger in there, it might just deglove you. Kind of like what happened to me back in high school. With this test, I want to demonstrate airflow and static pressure. So the idea is I want to see and show you how fast each of these fans fills up the bag. And then also I want to show you how hard it is for me to push the air back out through the fan once the bag's inflated fully. So let's discuss airflow. So basically in the US you'll often hear cubic feet per minute or CFM, which basically translates to how much air, what volume of air will something move in a minute. It's simple as that. You'll see the Delta fan fill the bag up demonstrably faster than the Noctua fan. Of course, it needs more time for the blades to spin up to full speed, but it still dramatically outpaced the Noctua. But I'm gonna argue that this isn't necessarily better in most cases, especially with gaming PCs. So with a gaming PC, the real challenge is the thermal mass of the heat sinks. In this case, I'm using a radiator, so the thermal mass is quite large, and there's a lot of surface area for fans to remove heat from. So the increased airflow and static pressure is probably not going to make all that much of a difference. I'm going to put this in my computer though, I'm going to wait for that. I'm putting this in there. But in general, when you're looking at fans for your cases and stuff like that, you're going to want to balance performance versus noise. You of course don't want something that's going to be so wimpy and weak that it's not going to cool your system, but you probably don't want to put this in there either, unless you want long-term hearing damage. Now pressure. Pressure is strange. It's often measured, and you'll see this in millimeters or inches of water, mmH2O. Measuring pressure this way quite literally means how high will this fan push or displace a column of water before it can't anymore. At some point, the weight of the water is going to be too much for the fan to overcome, so that stopping point is the fan static pressure. When I push on the bag in the Noctua test, it really doesn't take all that much to push the air back out through the fan. But with the Delta fan, the air is held in the bag much more effectively. I'm pushing fairly hard here. I didn't want to push too hard to put more strain on the motor and effectively draw more current than I can supply, but nonetheless, much harder to push the air out. But look at my Dell R720 server. Each of the bays here in the front is filled with drives, and the circuit board that connects the drives to the RAID controller, which is called the backplane, has only a few holes for air. So in a server, I'd trust fans like these to be able to cool things effectively a whole lot more than I would trust something like this. Now, something else I want to talk about are the guide vanes that you see on some fans. In this case, both the Delta and the Noctua have them, but what are they really doing? When you look at flow simulations of computer fans, you'll find that the exhaust of these fans spreads outwards as well as forwards. That's because of two things mainly. Number one, when the air is coming out of the fan, it's higher pressure in this area, but then lower pressure here where the air isn't being moved. So high pressure air will want to diffuse into low areas of lower pressure, so it's going to spread outwards a little bit. Also, this rotational motion forces air to the side of the fan. So when it exits here, it's going to want to keep traveling like that. And this outward velocity gets worse if you have filters and stuff here, because you're effectively making this area lower pressure, and the fan blade will take advantage of that and spin faster. So when it spins faster, but there's not actually enough air to go through, it's just going to keep getting pushed sideways. It's not great. So if you straighten the flow with these kinds of guide vanes, you're effectively increasing airflow, and you're helping that fan overcome obstacles in the case. And in a server, this represents a vast improvement because the air is less turbulent, it's straighter, effectively, it's much faster as well. But there is another way to do this, a very special type of fan. By the way, I hope you like the audio. I finally got myself a microphone. Here, look at this. Look at this guy right here. This is a counter-rotating fan. So there's one set of blades for the intake that go this way, and then another set that goes the other way. So together they kind of mesh like that, and they do a little bit of that. What might that do to the airflow, you're wondering? I actually found this on eBay, and I really wanted to get it, but like that's Oh man, that's kind of expensive and it's pretty far. Psych, my obsession's unhealthy. You can't stop me. I bought it. I got it. $100. I got it. It's mine. You can't stop me. Go ahead. Go ahead. I mean, tell me so about cool. Money. Go ahead. It's here. It came from. I had to buy it there. It took a month to get here, but it's here. Whoops. Oh yeah. Dude, what a monster. Why did I buy this? This was $100. There you go, that's the model if you want to get your own. 7 amps. What a purchase I've made. Let's talk about this, and luckily they kind of comes apart in two. Man, this, I can't get over how expensive this was. But all right, let's figure this out. So here is the intake fan, just removed. So there's the intake. Comes out here. What's the problem? The column of air here kind of starts getting pushed towards the edges. It starts expanding. High pressure here, low pressure here. Wants to move this way. The spinning of the blades also sort of flings the air to the side and then out that way. And like we talked about, it gets worse if there's obstructions at the intake. So if the fan spins this way, the blades are sort of shooting out that way. That's the sort of centrifugal motion that the air will be taking when it leaves this fan. So you use this fan to catch that air. The blades of the intake fan are, let's see, okay, so they're going this way, flinging air sort of like out in these directions, sort of that way. And then you take these blades and they say no. And then they scoop the air and they just they shoot it forward. I'm going to put this back together now. Now kiss. You're kidding me. So I've already severed a wire. Let me get some electrical tape. My God. I mean, watch. All right. I'm really excited to have one of these though, because this is what like a really beefy server would use. This thing can create just like crazy static pressure and airflow, and the airflow is like unbelievably straight. I think I might be able to like blow candles out across the room with this thing, just directional, just I'm gonna be an airbender with this thing. Yes, an airbender. Let me show you something. So of course you see my lovely candle over there, but what's this? A measuring tape. Oh, what's this? 13 feet, what's above it? Yeah, of course. I'm pretty sure this thing can do it. This is the power of a counter-rotating. Thank God. Ugh. All right. That's a counter-rotating fan. They're pretty cool. But yes, these are used in servers all the time for the big heavy power. Like take Linus's $1 million unboxing. That server that he uses, the AI sort of processing server, there's 8 NVIDIA A100 GPUs in there. Like, just think about how much air you need to cool those. Like, and also how much resistance you're gonna have too. Like, my God, you need some of these. Whoa!
Oh my God.
We have liftoff, ladies and gentlemen. So that server does. That server's got 4 of these. Not this one, but there's some 92 millimeters. This is 120 millimeters. This is kind of crazy. So let's go ahead and run the same test on this thing. And I'm pretty sure you're gonna be blown away by the results. God, am I gonna lose subscribers for that joke? Probably. Now I'm a little worried about this setup, and let me explain why. So it says that this power supply can handle up to 16 amps on the 12 volt rail, and this thing will only draw about 7.2 amps. So in theory, it's good, but also this is my engineering. And I don't know how much I trust my own engineering. I should trust it more, but you know. So at this stage, old Reliable here will be by my side at all times. Give her what it's got. You'll notice I've changed clothes. It's a completely different day. It's busy around here, but I get it done. Now I think this is gonna fill up the bag like really, really fast. I was right. Oh. So quite fast, and it's really hard to push that air back out. Whew. Well, my friends, the moment of truth has finally come. We're gonna throw these bad boys in this bad boy, and we're gonna see what the temperatures look like on this bad boy. Couple of things first. Hold on, bear with me. Sorry for the mess. It's Sunday, it's my cleanup day. Forgive me. Second, I kind of wanted to throw this guy in here. Oh, I thought it was going to be too big, but no, maybe I can do it. This fan, remember, this is the one that sliced my finger off. Yeah, mwah, love you. We made up. Oh, another thing. Let me get this bad boy opened up for you. Another thing. So before I do anything, I'm gonna unplug these two fans because they're gonna be like pretty much wind turbines with the amount of air that something like this is gonna throw at it. So I'll unplug these two. I'll also probably unplug these two back here just in case the airflow is like so great that it also spins these, which wouldn't surprise me, to be honest. Yeah, I can actually fit this fan. This is like an insane fan with both static pressure and airflow. And I mean, part of that is just due to the fact that it's quite a bit larger than a 120 millimeter fan. But yeah, I like this fan. You know, despite the fact that it cut my finger. All right, hey there. To start with, I have the, let me open this for you. So these are the two Foxcons that I had been running. They're 120 millimeter fans that draw about 0.9 amps each. They're not that loud, but I actually have a sound pressure level meter on my phone that's probably not the most accurate, but should give you a good idea of what the ambient noise is for this kind of thing. I'm gonna shut off my servers down there to get a more accurate reading. Anyways, here you go. Just like that. I never realized how pretty this is. Well, turns out this monitor's not up to snuff. I have no idea what's going on, but I also found this monitor in the dump, so that's probably a good explanation for you. Ta-da! This is another trash monitor that has dead pixels in 2 lines, but I can read the screen and I see, oh shit. Working mouse. Very exciting. So we're going to start it here and take a look at the max temperatures and the max clocks and all that. So let's go ahead and start a multi-core test. Now for something a little more sensible. Time for some Noctua. It's so much quieter, my god. So now it's time for the first actually powerful fan that I have right here, the Delta PFR 1212 DHE, I believe. I can't believe I memorized that, but I sure did. I also only have one of them, and I'm not willing to go out and buy another one because they are prohibitively expensive now. But in order to make sure that the pressure is consistent and doesn't just come back out through this door, I've taped up this opening so I can just kind of close it. No air will come in or out, and all's good. I also have the wires coming out of the top here. You know, clearly they're not terminated in a way that can just plug easily into the computer, but also I don't want to run this on the same power supply for just concerns of power draw and stuff like that. So we'll go here, we'll just do this. And inside the chassis itself, I have disconnected these two fans here, just in case this thing pushes enough air to spin those fans, which it most definitely will. I don't want any voltage feedback going to the motherboard. That can damage your PWM channel, your tachometer channel, just not a good idea. So it'll kind of just look like this for the test, but it should be fun. So here's what it's gonna look like after all is said and done. Yep, there she goes. And again, it's kind of hard to do that with the power supply on top here, but let's shut it up. Let's close it up and continue with the test. Yeah, that's not too great. Even just the noise makes me feel uneasy. It's way too loud. I hate it. I feel like I'm gonna need this. Like I just have to stand by with this at a moment's notice. I genuinely hated that. My power supply is hot. The fan is hot. It sounded like death. I couldn't tell if it was going to destruct itself. I mean, I do trust myself as an electrical engineer. But is that really wise? And I kind of don't want to do the other high power fans, but for you, I persevere. All right, time for the next fan. And this one I feel a whole lot more comfortable with. It's more like a 3 amp fan, and I have high hopes for this one. Yeah, oh, nice. And now the moment you've all been waiting for, but certainly I've been dreading, because this is a 7 amp fan, and oh man. Well, it also shuts the door behind itself. Oh my God. The suction. I think I hated that one the most. Everything just got hot. On this side of the radiator, it's still warm. On this side, it's ice cold. I mean... And now, to finally answer the ultimate question, which of these lovely fans am I gonna put in my PC? Predictable, I know. But I have data to back up my decision. I'm a bit of a recovering stats nerd, so please bear with me. There's a lot going on here, but we're gonna get through all of it. Let's start by talking about the experiment itself, because I've already made a few mistakes. The tests with the higher power fans are done with just one of the fans, while the Foxconn and the Noctua, I had 2 fans running, but they were running from the motherboard, which by default puts the fans at 60% duty cycle. So for the purposes of analysis, I'm going to do some normalization and standardization where I can to try and paint a more accurate picture of airflow and static pressure and how it affects our test scores. It's important to remember that 60% duty cycle doesn't mean necessarily 60% of the power in terms of airflow and static pressure. It's not quite linear like that, but we're going to just make the assumption that it is, because I figure the difference would be negligible since this applies to the lower powered fans. And all in all, when I talk about airflow and static pressure, I don't mean the airflow and static pressure of each individual fan. I'm talking about the airflow and static pressure of all intake fans going into the PC case, whether it's 1 or 2 fans. With that out of the way, let's look at our raw data. Here are my results for Cinebench R23, FarmArc at 1080p, and the static pressure and airflow generated by each setup. Remember, this is total airflow and static pressure, not just individual fans. Already, you'll notice that the benchmark scores are very close together, and that's what I want to dive into. Here, I have the results from my decibel meter. An important thing to remember is that decibels do not track linearly with perceived sound. Something at 50 decibels sounds twice as loud as something at 40 decibels, and there are a ton of nuances with how the human ear interprets specific frequencies that varies person to person. Here are my CPU temps, which were gathered over the course of a Cinebench R23 multi-threaded test, and here are my GPU temps, which were gathered over the course of a Furmark render test at 1080p. Remember what I said about the distribution of benchmark scores? Well, here's what I could show you if I wanted to try and sway your opinion that higher airflow and pressure are better overall. But if I include 0 in this range, things are really put into perspective. In order to get an idea of how small the differences really are, here's how each run compares to the average score for all runs. The deviation is consistently less than 1% above or below average. Now, let's look at how the fans perform in terms of airflow and static pressure. Here's a look at total intake airflow and total intake static pressure. We see that airflow and static pressure don't exactly go hand in hand, and here's a normalized graph to help illustrate that point. The most powerful fan was the counter-rotating fan, no surprises there, which produced both high airflow and high static pressure. But the large 150 millimeter fan was able to compete in the realm of airflow, but not static pressure. Here's a scatter plot of the same data if it's easier for you to visualize it this way. Because both airflow and static pressure make up a fan's capability to cool PC components, I've created an informal power index that evenly weighs airflow and static pressure together and provides a ranking, so to speak, for each fan. This scale is normalized from 0 to 1, where 0 is just nothing happening, no airflow, no pressure, nothing. And 1 is the most performant fan, again, the counter-rotating fan in this case, because it had the best combined scores in terms of airflow and pressure. I'll be using this index for other parts of my analysis, including sound performance. So, how much louder did we have to get for more air-moving power? Quite a bit, it turns out. Since this scatter plot is normalized, you can see that the fans get much louder for a small increase in airflow and static pressure, with the exception being the counter-rotating fan. It produced more power while being quieter overall, but remember that the design difference doesn't really play fairly with the likes of the Delta fan, which only has one set of blades. Counter-rotating fan has two. It's a little different. Also remember that decibels and perceived sound do not track linearly. The Delta fan in this scenario sounds about 7 or 8 times as loud as the Foxconn fans to our ears as humans, and prolonged exposure to noise above 80 decibels or so can lead to hearing damage. These aren't fans you want to be around for too long. I'll start by showing you my normalized scatter plot for CPU temperatures versus airflow and pressure, and my normalized scatter plot for GPU temperatures versus airflow and pressure. There's a much clearer trend line for GPU temperatures, but this is likely just due to the fact that the higher power fans were able to replace the warm air on the GPU with cool air more quickly than the lower powered fans. With the radiator being so close to the fan and thus so easily influenced by the different fan profiles, our CPU temperatures are a little more sporadic. But the point still remains. Even with these vast differences in airflow and static pressure between these fans, not much really changed across these tests. These differences in temperature are minuscule, and they're all at a level that the PC components can easily cope with without much difficulty. Remember, CPUs don't generally start throttling down in clock speed until they're in the 90s, so our performance across these tests didn't really take much of a hit, as we've seen. Therefore, airflow isn't as important as you might think. So let's just face the facts. Even though they look really cool, fans like these are just not suited for an application like this. I might be someone who's used to the constant drone of computer fans in this apartment. I'm looking at them right now, but it's just not worth it. I would get hearing damage after years of using this. I don't want that. I'm sticking with the Noctuas. I guess I ought to figure out what to do with all of these fans I got here. Maybe I'll turn this one into a hair dryer or something. Thanks for sticking around to the end of the video. I know it was a long one and it was very technical, but if you made it this far, probably means you're pretty interested in this topic, and it's a fun topic to explore. So thank you for your support. I'll see you next time. Be well. Read the screen and I see, oh shit. Dead mouse.